In this module, we'll go through logistic regression, making use of the linear regression model to better understand regression as a concept. We will continue to the Poisson model as a specific case of the chi-square test, but looking at spatial data as in mapping. The objectives of the presentation start with linear regression, drawing on those concepts to better understand logistic regression. Within logistic regression, I'll compare the approach we are using, which is exploring one exposure and one outcome, to a logistic model that tests multiple predictors together. Finally, we will talk about the Poisson model using the examples from the book. This figure is a simple linear regression. It is literally plotting the BMI of everyone in your sample on the x-axis, or the horizontal axis, against their systolic blood pressure on the y-axis, going vertically. The question in a linear regression is whether there is a line, and if so, whether the line has a slope that goes up or down. Here, the slight slope of the line indicates that a higher BMI is associated with a higher systolic blood pressure. The relationship between BMI and systolic blood pressure can be expressed as a mathematical formula that relates to the line. The beta naught is called the intercept. It is simply the starting point. Taking a low BMI level, say 20, as our starting point, would be a systolic blood pressure of 118 as a starting point. This is what you see where the line intersects with real values. Notice that the scale of the plot only starts at a BMI of 10, and you don't see any observations until closer to 15. In a linear regression, you sometimes get a better fitting line by adding in more variables. This is a second regression line, which includes not only BMI, but whether or not the person has health insurance. So in addition to BMI, not having health insurance is associated with adding 2.4 points to the systolic blood pressure, in addition to BMI. In logistic regression, we aren't trying to get the best fitting line, we are trying to estimate the odds ratio. We use a logistic function, and because we are using a function, SPSS gives values associated with the exposure, but it also gives the constant. This is not a meaningful measure, it is simply a starting point for the regression line. The B is the beta coefficient associated with either the exposure, which is of interest, or the constant, which is not. In addition, adding a confounder to the model, we are only interested to see what happens to the main exposure. So look to see if the B of health insurance changes. As confounders, I'm using an example of adjusting for different BMI classifications, with normal weight as the comparison. In this new model, I'm not interested in the B or beta coefficient of BMI classifications, or even their statistical significance. I am interested in the B of the main exposure, which is health insurance. Did that B, beta coefficient in the logistic regression, change by more than 10%? Something that we aren't making use of in this class, but an essential fact to know for the future, is that continuous variables can be entered into a logistic model, but they have to be tested first for linearity in the logistic, and by extension, linearity in risk. If you look at the B values for increasing levels of BMI classification, you see the BMI goes up in an almost linear way. For example, there's an increase in risk of 0.2 or 0.3, but the jump from class 3 to class 4 is much higher. So there is a progressive increase, but it is not quite linear in the logistic. Here you see again that the odds ratios increase progressively, but you see a greater magnitude of change in the last odds ratio for the highest class of obesity. So the odds ratio goes from 3.7 to 5.5. The reason why linearity is important is the meaning of the interpretation of the final result. Here I'm showing a logistic model with BMI entered simply as continuous. The B and the E to the B, or the odds ratio, can only be interpreted as the change in risk or odds associated with every unit increase in BMI. If that risk changes at one end of the spectrum or even in the middle, the conclusion about the relationship between BMI and high blood pressure would be wrong. Here, the interpretation would be that for every unit increase in BMI, there is a 1.07 increase in hypertension. But in the earlier model, we saw that the risk does not increase steadily, but jumps in the higher weight class categories, implying that BMI and high blood pressure are not linear in risk. However, if you leave the categorization in dichotomous groupings, or even categorized as done below, the rules of the logistic model are not broken. So the take-home message is that if you aren't sure if there's linearity in risk, enter the variable as a dichotomous variable or as multiple dichotomous variables with the same reference. I'm going to briefly describe a concept called relative identified distribution, or RIDIT, and this is a process of using statistical methods to identify comparison groups. This is not something that we're going to do in this class, but I want you to be familiar with this concept so that later, if you need to draw on it, you understand how it works. First of all, RIDIT is not needed if all the groups are clearly dichotomous. So this is why we're using dichotomous variables in your logistic analysis. Also, it's not needed if risk clearly increases in a linear fashion. So if you have increasing risk by levels of income, you don't need RIDIT. RIDIT can help to clarify the groups with the strongest contrasts, and it does that based on probabilities, where you have a 2 by k table, and k is ordered from low to high in terms of a risk relationship. RIDIT is a process where 0.5 is the concept of a probability that this group is equally likely to be to the left or to the right of the comparison. And the concept of a RIDIT of less than 0.5 actually means being better off, because that is a concept that they will have a lower risk relationship compared to the reference. How do you use that actually? So here is an example that's drawn from the book. This is on page 178. And what this means is each of these are the RIDIT comparisons. 0.46 is showing that the non-smoking, less than 55-year-old females are less likely to be in a low socioeconomic status group compared to the non-smoking females who are greater than 55. So we have one comparison group, and each of these probabilities says something about risk. And what we're looking to see is it the less than 0.5 or is it greater than 0.5? So all of these categories, given in order, are less than the 0.5 cutoff. And if you look at the confidence interval, they're all less than the 0.5 cutoff. However, they're not different from each other. So what you're looking for is, do the confidence intervals overlap with each other? And in this case, all of the confidence intervals here overlap with the other groups. And so that's what you're doing with a RIDIT analysis, is you're comparing not just the 0.5, in this case it's less than 0.5, and you're also comparing whether the confidence intervals overlap with each other to see whether the groups belong together or not. Our main focus is on the logistic model and an epidemiology that is most often focused on exploring a single exposure in relation to a single outcome. Other variables, such as confounders, are usually entered to better understand that association. We have already discussed the model focusing on a single exposure and outcome, but there is a second approach that is also used, and you may see it in the literature. It is called a prediction model, by which logistic regression is used to identify the most important risk factors associated with a given outcome. In this approach, multiple potential risk factors are explored. They're tested first one at a time, usually based on a p-value cutoff, are included in the model after selecting the appropriate contrast between groups, see RIDIT or odds ratios. The purpose of the predictive model is to identify which risk factors are most important. Prediction models are hypothesis building and/or can be used to identify the risk groups most in need of intervention. Although you aren't running a predictive model in this class, it can be helpful to know the approach. After selecting the variables that are significantly associated with the outcome, in what we refer to as a univariate approach, in other words, one variable at a time, they will be entered in the model progressively, one at a time. First, it is important to note that the p-value for inclusion or exclusion is often a broader criteria for a logistic model and can be a p-value of 0.2 or 0.1. Usually the broadest criteria is used for the initial inclusion. The variables selected are then entered one at a time in what is called a forward selection, in which the p-value of all variables are being noted with every new variable added to the model. Only the variables that meet the p-value cutoff are kept, and once the model is built, it is tested again with a backward selection process to ensure that the order of variables entered does not influence the decision for inclusion. Often, if two variables are strongly correlated with each other, they will not both appear to be significant when they are in the model together. Such variables should be entered and taken out to facilitate the decision of which of the two variables to include. Looking at this model, if it were a predictive model, I would include all of the variables, but the variable did not get medical care because after including all of the others, this variable is no longer statistically significant. See, the p-value or the column for significance is 0.728. If I were just looking for the exposure, no health insurance, the example from your assignment, I am interested in the crude association, which is shown here. And I'm interested in seeing whether or not it's confounded. Here I would say that biological sex is a confounder because the B changes from 0.32 to what it is here, 0.43, which is more than 10% change. However, before skipping right into the logistic model, I should have stratified it by 2x2 tables. And if I had done that, I would have seen the evidence of effect modification. If I stratified my odds ratios and see that the two odds ratios are different from each other, I want to check if the differences between the odds ratios are enough to consider effect modification. In order to test an interaction term, I need to enter the exposure, effect modifier, the interaction term, all together in the same model. Adding the interaction term with exposure and outcome, coded as 1, tests the probability that the natural logarithm of the odds ratio, or the B, of being male and being overweight is associated with hypertension independent of being male separately or of being overweight and not being male. In a logistic model, other variables are only included if they change the B greater than 10%. In this case, the only variable from the example given is a variable that you will test later as an effect modifier. Given this example, those with no health insurance are 1.37 times more likely to have high blood pressure, and the association is statistically significant. In your exercise, you will explore for confounding and effect modification that were not included in this PowerPoint, so you will have a different result. The predictive model would keep all variables that are significant, and we would interpret the result of the model below as identifying risk factors that would go into our final model: not having health insurance, having a higher BMI, and being male. So, in summary, in a predictive model, there is no concept of confounding. All variables are adjusted for the others, but the concept of confounding is related to understanding a single exposure and outcome and whether that result is clouded or confounded by a third factor. Because there is no single focus on one exposure, inclusion in the model depends on the p-value in relation to the outcome, which also relates to building the best fitting model. If interaction is found, stratify the final results. If interaction is found, two or more adjusted models in the analysis exploring a single exposure will be your final result. The interaction term only clarifies the association between the exposure and outcome in a predictive model. and it creates better, more predictive models. Of course, there is more to learn about logistic regression, but there are other types of regression. One of these that you may read about is Poisson regression, and it is used to test spatial clustering. Obviously, spatial clustering is important for geographic mapping, identifying the source of an outbreak, identifying environmental risk factors and/or risk factors related to a neighborhood or zip code. Mapping clustering of risk can help to identify environmental factors associated with, for example, malaria, identify health risks related to neighborhood and zip code, and test clustering in the occurrence or the probability of illness in a district, state, or even country. In order to illustrate the idea behind Poisson regression, I'll use the example from the book. In the example, the authors give a square with 200 points generated at random over 100 squares. Is there clustering? The Poisson regression asks this question by posing the null hypothesis. Is the distribution at random? The p-value will tell us how likely it is that the clusters are distributed at random. If that chance is very small, we reject the null and conclude with 95% confidence that the result is not random chance. So how does it work? Here I'm laying out the example as given in the book to show where they get their numbers from. In Table 5.1, they use the example of 200 hits, marks or counts, and 100 squares. The average hits per square would be 2. Probability estimates are determined based on the mean value of hits or counts and the number of subdivisions. So here is the formula as written in the book. Although it looks complicated, it is really quite simple. The lambda symbol represents average hits, which is 2. This is simply the instances of occurrence over the number of spatial blocks, the squares in this case. If the hits were perfectly random, each block would have 2 hits. So, filling in the numbers for the formula all the way down, these are the probabilities of the square of having 0, 1, 2, all the way through 7 hits. It makes sense that the greatest probability is between 1 and 2 hits, and the smallest probability is 6 or 7 hits. The formula is the mean, taken to the power of the number of hits divided by the number of hits, factorial. The factorial is a concept of multiplying by each of the subdivided numbers. So 1 factorial is 1, 2 factorial is 2 times 1, 3 factorial is 3 times 2 times 1. So it is simply progressively going down, multiplying by each of the numbers, counting up towards that number. Here we see the table from the book relating to the number of squares that have 0, 1, 2, 3, up to 7 hits. The first row reflects the number of squares that had the given number of counts, ranging from the 15 squares with 0 hits to the 1 square with 7 hits. The second row shows the proportion, e.g. 15 out of 100 squares is a proportion of 0.15. They used a total of 100 to make it easy to follow the math, so 15 squares is a proportion of 0.15. The probability of no hits based on the formula is 0.135, which, when applied to 100 squares, would be an expected count of 13.5. The third row is the probability calculated in an earlier slide, making use of the formula for the probability given in the book. The probability, it is easy to get the expected counts. Given a probability of 0.135, we would expect 13.5 squares to have 0 hits. Probability can be seen as a proportion by multiplying it by the total you get to get the expected number of counts. Note that the formula is not realistic. There are no half squares, but this is based on the mathematical formula. The Poisson model tests the probability of observed in relation to expected. One of the assumptions of the Poisson model is that the sample variance will be equal to the mean if the distribution is random. The way of testing it is by way of the p-value. So how do you interpret the p-value from your Poisson model? Testing the probability of no spatial pattern. So the probability that the variance seen, in this case 2.081, is not different from what is expected, 2.0. The null hypothesis is there is no difference. The probability of no difference in this case is 0.372. So when you see a probability of 0.372, you would say no difference is actually a likely probable explanation. So we don't reject the null hypothesis of no difference, and we accept the likelihood that there is a difference.